Welcome to not the fourth video. I forgot to put 4.5. So welcome to kind of an intermediary video, an in-between video after episode or after video 4 and before video 5. I was gonna make this video. So this one will deal with a little bit looking at Weyl spinors. You can see I've written out some stuff already. We're going to be working with the algebra of physical space, G3, which is generated by three mutually orthogonal unipotent vectors, so positive squaring. And the entire algebra is encoded with this basis. You have the scalar, vectors, bivectors, and trivector. Because the trivector commutes with everything in this algebra and it squares to -1, it's traditional to denote it as I. And so you can also use what's called the Pauli representation. So the Pauli representation chooses the Z axis as a spin axis, and all the rest of the matrices kind of fall out of that. So you can have this is the matrix for one, for all the vectors, for the pseudoscalar, so for the trivector here, and then for the bivectors. Now there will also be some operations that are used in this, and one of them is grade involution, and in G3 can also be called parity because it corresponds to parity in quantum mechanics. And it just switches the sign of the odd or of the odd, whatchamacallit. It swaps the sign of all of the odd blades or multivector, all the odd vector k vectors. And then the reversion, which reverses the order of products. And so that reverses the sign of bivectors and trivectors. And then Clifford conjugation, which is a combination of both. When you combine negative with positive, you get negative. Positive with negative, you get negative. Negative with negative, you get positive. So you have Clifford conjugation, which is the composition of reversion and grade involution. So we'll also have something called spin projectors, and they project along a certain spin axis. And this is what their algebraic form looks like. And this is what their matrix representation looks like with the Pauli representation. This corresponds to a projector for a left projection, and this corresponds to a right projection. And when you represent a multivector, if you if you have some general element in the algebra G3, and you multiply it by this projector, you end up with a left Weyl spinor, where you end up with a matrix representation like the one I'm writing here. You end up with the spin up component and the spin down component like this. So spin up, spin down, spin up, spin down. Then if you multiply some element by the other projector, then you get a right Weyl spinor. So like this, which then is 0, 0, and you get the spin down, right, spin up, right, where you can see that this has spin down components, this is spin up components. Then you also get what are called dual left Weyl spinors through this geometric operation. I'm not going to derive it, I'm just giving it here. And then this has a matrix representation. Here, I lost my place in the page where I have it written. This has a representation like this. where you have negative spin down left, and then spin up left. And then this has a matrix representation where you have on here we go. Yes, where you have oh shoot, did I write the wrong thing? No, I didn't. I'm good. Okay. I'm just not sure which coefficient to write here. Shoot. 1 second while I look at I should have prepared this before the thing so I don't have to think about it now. But you get 0, 0, spin 1. Yeah, okay, so you get this. And negative spin up. Right. Okay, so that's what you get. So you can have a left vial spinner, a right vial spinner, a dual left vial spinner, and a dual right vial spinner, which just look like you have a column spinner, row spinner, row spinner. And you also don't need to know exactly what these are, but it satisfies a symplectic product, and these are all examples of the symplectic product. So you multiply these together, and then you take only the zeroth component. So, or a zeroth component, you take only the scalar value of this product. So you can see that this is a left vial spinner times a dual right vial spinner, and then you have a dual left vial spinner times a right vial spinner, then left vial spinner times a dual right vial spinner, right vial spinner times a dual left vial spinner. And this product also has another property that, namely, if whatchamacallit. Oh, hang on. I did write down the wrong thing here. You end up, yeah, I did write one of the wrong things down here. So, that's instead of rewriting all of this, I'm just gonna delete it. Well, it's a good thing this isn't one of the main videos, because this is just kind of a mathematical aside. Okay, then get this like this. And what this does is, oh shoot, okay. What this does is you have to take a dual, you always have to take a spinner, and then you always have to take a left spinner and then a right spinner, but then make the right spinner into a dual right spinner. Um, and then you have to conjugate it using grade involution, because what grade involution does, remember how I said it's parity? Physically, this corresponds to turning a right spinner into a left spinner. And you can only compare spinners of the same type. So what you do is you take a right spinner, make it dual, and then convert it into a dual left spinner. And then the dual left spinner that is represented by this entire thing interacts with this, and then you take the scalar product of it, and this is the symplectic product. If which has the condition, which has the condition that if If sigma x, if this right here is proportional to if it's proportional to the dual left spinner, then uh, this thing right here is equal to 0. Yeah. So you end up that if the right spinner, when transformed into a left spinner, ends up being proportional up to a real constant of a left spinner, then the product goes to 0, which is the same thing as saying, like, if you compare a spinner with its dual. So this is the same thing. This is the same as saying that when you compare a spinner with its own dual, then you get 0. Okay, so this was just a really kind of rough crash course into how Weyl spinners work in geometric algebra. So let's now take all of this, all of what we've learned from this, and look at conventions that are used in traditional non-geometric algebra approaches to Weyl spinners. In the Vaz and Vaz Junior convention, there are what are called, you end up with what are called contravariant, contra, undotted spinners, and then you get covariant, undotted spinners, and then you have contra dotted spinners and covariant dotted spinners. So in this convention, the contravariant undotted contravariant spinner has an index like this. The covariant has an index that's lowered, and the covariant and the contra has something that's raised, something that's lowered. And the key thing is that if you have a spinner that is contravariant, you need to consider products like this. Or products that look like this. And you can see that there are two definitions. Like, you have something that is undotted, or they both have to be either undotted or dotted. And this is basically the same thing as saying either left, or right, because you can only compare left with left and left with left or right with right. So the way that people this convention switches between uses the following property. You have a spinner, and then you take the grade involution, which in this case corresponds to a complex conjugate. You end up with this right here. So that's how it's lowered. and lowered and becomes dotted. So the difference between the two formalisms then is actually that in the van der Waerden formalism, it swaps the definition of contra and covariant. So this actually becomes co. Okay, so the contravariant is up, and this is down. But before in this formalism, man, I'm really not doing the best job of explaining this. Luckily, like you can pause and do other things, but and I also have a write up for this, but this is where the definition is made in this convention. They define the spin up with this right here. But in the van der Waerden convention, it's actually right here. Because this right here is defined as the right. This is defined as the right. So you can see in the Vaz Junior convention, the left left Weyl spinner is associated with the contravariant spinner, and the right Weyl spinner is associated with the covariant spinner. However, in the Van der Waerden convention, the the covariant spinner is associated with the left Weyl spinner, just like covariant spinners are associated with the right Weyl spinner. So this one uses contravariant for left and covariant for right, and then this one uses covariant for left and covariant for right. What this corresponds to is that if you have a spinner and then you apply grade involution, then you keep the same you stay contravariant, but you add a dot, so you go from left to right. So this goes left to right, and from up or yeah, so from up to down on the index. So goes left spinner to right spinner, also up and down on the index. And then this one goes left to right, and also and it like up stays up. Likewise, you can say down stays down. Mathematically, both of these conventions deal with this. So mathematically, they are the same. They're dealing with the same mechanisms, but they use different index conventions. Hopefully that made at least a little bit of sense. I should not have just free-birded it like this, but there's also the write-up, and I'm free to answer any questions on it because I assume there will be lots.